Welcome to the first lesson of module 4, which is on torsion part 1. In fact, if you remember that we had discussed in the last 3 modules which are on aspects of stress, strain and application of stress and strain on thin walled pressure vessels. Now, if a bar is subjected to an axial pull, it is subjected to a normal stress, which we have seen as load divided by the cross sectional area. Consequently, we have seen that if the bar is subjected to axial pull, it undergoes deformation, which we have defined in terms of strain, the deformation to its original length. Now, in this particular lesson, we are going to look into that if this particular bar is subjected to another kind of forces, which we term as a twisting moment or torsion, then what are the effect of torsion on such bars. So, it is expected that once this particular lesson is completed, or once someone goes through this particular lesson, one should be able to understand the concept of twisting moment and its effect on bars of circular cross section. Now, here we will be concentrating at the moment on the bars which are of circular cross section, and in this particular lesson we will be looking into the bars for solid circular cross section. Also, one should be able to understand the concept of shear stress which gets generated due to torsion, and one should be in a position to evaluate stresses and deformation in solid circular bars which develop due to torsion. Hence, the scope of this particular lesson includes the recapitulation of previous lesson, as we do in other lessons we have done, that we will be discussing the questions which I have posed last time in the form of answers, so that we can recapitulate the previous lesson. We will be deriving the formulae which are necessary for evaluating the stress and the deformation in bars of solid circular cross section, which arise due to the application of the twisting moment or the torsion, and then we will be looking into some examples for evaluation of stresses and deformations in solid circular bars. Now, let us look into the answers of the questions which I had posed last time. In fact, the last lesson which was the last lesson of the third module, where we were discussing the aspects of thin walled pressure vessels, and we had set some questions related to that. Now, the first question which was said was, how will you define a thin walled pressure vessel, and that is important because the previous module was devoted on this, that a thin walled pressure vessel. So, you should know how to define the same, and the thin walled pressure vessels may be defined in this particular form, that basically the pressure vessels are the closed pressurized containers, and these pressure vessels, when they are subjected to internal pressure, they are subjected to stresses. Now, we qualify these pressure vessels as thin walled, and that is why we call these as thin walled pressure vessels. Now, when the thickness of such vessels are sufficiently small, the thickness of the wall is sufficiently small compared to the radius of the container, so that the stresses are almost uniform throughout the thickness, and this is what is very important, that across the thickness of the pressure vessel there is no change in the stresses. If you look into the across the thickness, the change in the stresses is significantly small, and that is the reason we call this particular type of vessels as thin walled vessels. And when we talk about, and this is what we term as thin walled vessel, and it has been observed that if the radius to the thickness ratio, r by t ratio, is greater than or equals to 10, then this stress distribution across the thickness of the wall, across the thickness of this wall is significantly small. That means, we presume that the stress everywhere is same or uniform, we consider that as a thin walled pressure vessels. So, to define precisely, then we should say that when the thickness of the wall is sufficiently small compared to the radius, so that the stresses are almost uniform throughout the thickness, then the vessels are termed as thin walled pressure vessels. And the criteria is that if r by t, or the radius to thickness ratio, is greater than or equals to 10, then we call that kind of vessels as thin walled pressure vessels. Now, the second question posed was, what is the nature of stresses in thin walled pressure vessels? Now, in case of thin walled pressure vessels, the nature of stresses in thin walled pressure vessels is tensile. In fact, if you remember that we had discussed the type of stresses that gets generated in the pressure vessels, they are basically the tensile stresses which occurs on the surface, and we have seen in case of cylindrical pressure vessels, it is tensile stress along the circumference we have called as circumferential stress or hoop stress, and in the longitudinal direction we have stress which is longitudinal stress, and both the stresses are tensile in nature. And so as in case of spherical vessels, where we have seen the stresses which gets generated in any direction, they are tensile in nature. So, the stresses which develop in thin walled pressure vessels, they are tensile in nature. Now, the last question which is posed is, what is the relation between the volumetric strain and maximum strain in spherical vessels? Now, let us look into this in light of the discussions which we had in relation to the derivation of the strain. Now, you remember that the volumetric strain E we had defined as the change in the volume to the original volume, which is defined here as E equals to delta V by V. Now, this we had derived that the radius r, because of the pressure, it undergoes deformation and becomes r plus delta r, and thereby the change in the volume because of r plus delta r over the original volume gives us the expression for the volumetric strain epsilon, and which we get as 3 times epsilon r. Epsilon r is the normal strain which is developed because of the stresses in the spherical vessels. As you have seen that if you take a small element, we have the stresses developed into it in any direction which is equals to sigma. Hence, the strain at any point we can write as sigma by E minus mu times sigma by E, this being biaxial in nature. So, this becomes epsilon is equals to 1 minus mu by E times sigma, and in place of epsilon this is what has been substituted over here, and this is what you see over here, 3 into 1 minus mu sigma by E. So, this is 3 epsilon r, and sigma being P r by twice T, if we substitute that, then it becomes E as equals to 3 P r into 1 minus mu by 2 times T E. So, basically the relation between the volumetric strain and the normal strain is E is equals to 3 times epsilon r. So, this is the basic relationship, and finally, we arrive at this expression in terms of the pressure, the radius of the vessel, Poisson's ratio, thickness of the vessel, and the modulus of elasticity. Well, then, having known these aspects of the previous lesson which we discussed in terms of the pressure vessels, that what is the nature of the stress we generally encounter, how we define a thin walled pressure vessels, and then the relationship between the volumetric strain and the normal strain in a spherical vessel. Now, let us look into that if a bar, which we have seen in the past for the first 2 modules, that if the bar is subjected to an axial pull, it is subjected to a stress which we have defined as normal stress, which is nothing but equals to the load applied divided by the cross sectional area. Likewise, in the second module, when we have looked into that if a bar is subjected to a load, it undergoes strengthening, elongation or compression or shortening, which we have defined in terms of strain, which is deformation to its original length. Now, let us look into that if we have a bar which is having a circular cross section as shown over here, the cross section is a circular one, and also the bar is a solid one. Now, if a bar is subjected to a load of this particular form, which we generally call as a couple of the forces, say these are the forces which are acting, one in this direction and another in this particular direction. Then if we say that different distance between these two being d, and if we call the force applied is P, then this particular bar which is fixed at this particular end will be subjected to a moment which is like this, the magnitude of which will be P times d. Now, this particular moment is acting about the axis which is perpendicular to the cross section, which is if we call this as our x axis, it is acting about the x axis, other two axes being y axis and the z axis. Now, when a section or a particular member is subjected to a moment about the axis which is normal to the cross section. Now, let us say this is the cross section of the bar and this is the axis system which is in the plane of the cross section. Now, the moment which is acting over here is about the axis which is perpendicular to the plane of this board. So, if this is the axis, the moment is acting about this particular axis, and this is what is called as twisting moment or torsion. This we define as twisting moment or torsion. Now, we do calculate here the relevant formulae on certain assumptions, and these assumptions are that the circular sections, the cross sections remain as it is, it does not deform, and thereby there are no strain in the cross section. There is no change along the length of the member, and hence there are no deformation and there are no strain along the axis of the member. Only because of this application of the twisting moment, the cross section undergoes rotation, and that deformation we define in terms of the rotation of this cross sectional part. Now, if this particular member is fixed at this end, and if we take one length, let us say on this particular surface, then we will see that because of this application of this twisting moment, how it rotates, and thereby what is the consequence of that. In fact, before we go into that, let us look into another kind of loading which we have applied over here. Now, we have another load, let us say is applied in this particular form. Now, this is also a couple which is acting at a distance of, let us say this distance being d again. So, this is also going to cause a twisting moment or a moment about the axis which is perpendicular or along the length of the member, which is in this particular form, which is acting in a clockwise direction. So, this is also twisting moment, but the direction of this is different from the direction of the first one. Now, let us look into these two directions and analyze it. Now, in the first case, when we had the moment which was acting about the x axis and it was acting in an anti-clockwise direction. Now, if you look into this particular figure where this is the axis and the moment, the twisting moment is acting in an anti-clockwise form. Now, here it behaves in the form of a right hand screw. Now, if the moment is acting in this form, the direction of the axis is towards the thumb. Now, this is what we call as a positive twisting moment, where the direction, the vectorial direction is in the x direction. So, the moment is acting in the bar in the form where the thumb is directed towards the positive x axis, and this we call as positive twisting moment. Whereas, when we consider the moment is acting in a clockwise form, the thumb goes towards the opposite to the positive x direction, which we call as the negative twisting moment, and corresponding rotation as a negative rotation. Hence, if you look into this particular figure where we have the twisting moment acting in a clockwise form and the vectorial direction of this twisting moment is opposite to the positive x direction. So, this is the negative twisting moment and this is the positive twisting moment. That is how we define the convention of this particular twisting moments or the torsions. Now, we can either represent in terms of this twisting moment, or we can represent in terms of this vectorial notation, and both the notations represent the positive torsion. Or consequently, for this we can either give a twisting moment in this form, which defines as a negative twisting moment, or a vectorial direction notation in this form, which also defines as a negative twisting moment. Now, let us look into, before we go to the units, now this is how it gets rotated when a bar is applied a twisting moment. A bar which was initially straight, you observe that how it is getting rotated. This end being fixed, it moves and then forms an angle over here. Please note over here, there will be this particular original radius is getting changed, or this there is an angular change over here, and this is what we will be looking into in deriving the formulae for the torsion. Now, coming to the units of the moments. Now, here the force is applied in terms of Newton, or the unit of the force is Newton, and the distance being written in terms of meter. So, the moment, the twisting moment which we have, the torsional moment, this is defined, or unit of torsional moment is Newton meter. Well, now let us look into this particular configuration, where a bar which is again a solid circular bar, the cross section is a circular one and it is solid, it does not have any hollowness in such system. Now, if this particular bar is subjected to a positive twisting moment, then what happens to this particular system? Now, let us look into this. Let us call that we have one length on this particular bar, which we call as AB, and mind that this particular bar is fixed. Let us call this point as B. Now, this is fixed at this particular end and it is subjected to a twisting moment T at its end. Now, because of the application of the twisting moment, as we said that it will undergo rotation and this helix line will be formed, and thereby if this is the radius which we call as radius r of the cross section, will simply change and there will be a deformation angle, which this angular deformation we call as theta. So, because of the application of the twisting moment, the radius vector changes. Because of this twisting, the angular section moves and there is a change in the angle which we call as theta. Now, there are some assumptions which we make for this. Let us look into that before we discuss this, that circular cross sections remain plane and perpendicular to the axis of the shaft. Now, there is no change in the circular cross sections and they remain plane, they remain as it is before the application of the twisting moment, and thereby since there is no change in the cross section, there is no deformation, hence there is no strain developed into the cross section. So, cross sections do not deform and hence there is no strain in the plane of the cross section. Secondly, the distance between cross sections do not change and hence the axial strain is absent. Now, along the length of the member, since there is no change in the length of the member, so there is no deformation and thereby there is no strain in the axial direction. So, these are the assumptions we make, based on which we derive to find out what will be the relationship between the twisting moment and the deformation. Now, let us look into how do we derive the relationship between the twisting moment and the angle of rotation. Now, as I said that because of the application of this twisting moment, the length which was originally straight forms this helix and thereby there is a change in an angle, and this we have called this as theta. Now, if we cut a segment from this particular length, let us call this as length dx, which is designated over here, the distance dx. Also, what we do is that out of the whole circular bar, we cut off some top portion and take a smaller core, okay, and the smaller core, let us assume that the smaller core is having a radius which is rho. Now, originally this particular bar has the radius r and the core which we are looking into has a radius rho. Now, if we concentrate our attention on this particular segment, let us say this is A B and this as C D. So, A B C D or A B D C is an element on the surface of this particular cylindrical part or the circular body. Now, when this is subjected to twisting moment, then the radius which is line joining from center to B undergoes rotation. Now, since this is a small distance dx, let us say that the change in angle between these two segments of the cross section is also small, and let us call that as d theta. So, this rotation let us call this as d theta. Now, if we look into the distance on the surface of this particular body, now B moves to this particular point which we call as B dashed. Now, the distance B dashed, if we look into from the cross section point of view, the radius is rho and the angle is d theta. So, B dashed is equals to rho times d theta. Also, the distance if we look from the surface, now the segment ABDC undergoes changes on the surface in this particular form. Hence, there is a change in the angle. The ABDC element, because of the twisting moment, has undergone deformation, and there is change in the angle. And as we have seen in the past, that this change in the angle on the surface, we call this as a strain angle, which is gamma. So, if this is the strain angle gamma, this is gamma, and this distance being dx. So, distance B dashed again can be written as gamma times dx. So, if we equate these two, gamma dx is equals to rho d theta, then we can write gamma as equals to rho times d theta dx. So, this is the shearing strain which is written in terms of the rotation, and d theta dx we call as rotation per unit length. Now, as we know from Hooke's law, the stress is proportional to the strain, and so tau, the shearing stress, is related to the shearing strain through the shear modulus G. So, tau is equals to G times gamma, that is the Hooke's law. So, tau is equals to G times gamma. So, if we substitute for gamma, which is rho d theta dx, then expression for tau becomes G times rho times d theta dx, or this we can write as G d theta dx times rho. Now, if we look into this quantity G d theta dx, it is independent of radius, and as a result the shear stress is linearly dependent on the radius rho. So, it varies linearly from the center to the outer surface, and the stress becomes maximum on the surface of the cylindrical bar and is 0 at the center. Since it is varying linearly with rho, so along the section, if we look into at when rho becomes r, which goes to the surface, and thereby we get the maximum stress. So, if we look into this particular figure, so this is the central part of this cross section, and this is the radius vector here, which is r. Now, at a distance of rho, which we have considered in this particular configuration, which is rho. So, the shear stress is tau, which is given by G d theta dx times rho. Now, this when goes to the surface, it becomes the tau max, and this tau max is equals to G d theta dx times r when rho becomes r. So, that is the maximum shear stress. Now, if we look into an element, if we look into an element which is taken out from here, now this particular element, as we have seen, has undergone change in the angle, which we have called as strain angle gamma, and consequently it will be subjected to the stresses which we are calling as shearing stress tau, and complementary will be in the perpendicular direction. So, this is the stress that gets generated on the surface of the cylindrical specimen or a bar which is of circular configuration. Now, what we need to do is to find out the relationship between the twisting moment and the stress, so that we can evaluate stress in a bar when it will be subjected to a twisting moment, and that is what we call as the torsion formula, the relationship between the torsional moment which is acting on the bar and consequently what is the stress that gets developed on the bar. Well, these assumptions we have seen already, and now let us look into that. What we have seen now is the compatibility criteria. When the bar is subjected to a twisting moment, it is undergoing deformation which is in terms of the rotation, and we have related the deformation to the stress. Now, let us write down the equilibrium equations, so that we can write down the relationship between the stress and the corresponding twisting moment. Now, the equilibrium criteria demands that the resultant shearing stress which will be acting on this surface, that should be equals to the twisting moment that is being applied in the section. Now, the twisting moment that is applied is the T. Now, when we are applying this twisting moment, the shearing stresses are generated. Now, this is the center of the cross section. Now, let us take an element on which the area is dA. So, the force that will be acting, which is perpendicular to this radius, is equals to the stress times the area. So, if we say the force which is acting on that small element as dP is equals to the stress tau times area dA, and we have already seen tau is nothing but equals to g d theta dx times rho. This is what is the stress on this element which is at a distance of rho from the center times dA. So, the moment which is the resistive moment that is being applied by this particular element will be the force multiplied by this distance which is rho. So, the twisting moment T which is acting on this particular cross section is nothing but the summation of all such forces over this particular cross sectional area, which is integral dP times the distance rho. So, this is equals to integral over the area. Now, dP if we substitute in terms of this, which is g d theta dx times rho, and rho times rho becomes rho square times dA. So, that is what is the twisting moment that is applied in this particular cross section. Now, g d theta dx being constant parameter, let us take that out, and this is equals to integral over A rho square dA. Now, you can recognize this particular term, rho square dA is the second moment of this smaller area with respect to the axis which is passing through the center of this particular cross section, and as we know that this is nothing but is the moment of inertia of this particular section about the axis which is passing through the center of this cross section, which is perpendicular to the plane of this cross section. So, this we generally designate as J, and J we call as polar moment of inertia, is polar moment of inertia, and as you know this is the sum of the moment of inertia in x and y axis. So, J is nothing but equals to I x plus I y, where I x is the moment of inertia of the section about if we call this as x axis and this as y axis, and the perpendicular direction if we call that as z, which we have designated x here, is the moment sum of the moment of inertia in the planar part, which if we add it up we will get the moment of inertia which we call as J, the polar moment of inertia. So, this particular expression for torsion then is equals to G times d theta dx times J. Now, this if we try to evaluate that what is the rotation over the entire length of the bar. Now, the bar we have seen that the twisting moment which is applied is related now to the rotation per unit length in terms of the polar moment of inertia of the section and the shear modulus. Now, if we like to find out that the bar which is fixed at one end and subjected to twisting moment on the other, now what is the change in the angle or the change in rotation over the entire length of the bar. Now, if we like to compute that, now let us evaluate. Now, we have seen T is equals to G j d theta dx, or d theta is equals to T by G j dx. Now, if we integrate these over the entire length, then we will get the rotation between the two ends, and this is the theta is equals to integral dx gives us the x and the length L. So, T L by G j. So, this is the deformation of the member which is subjected to a twisting moment, and the deformation is in terms of the angular change which is the rotation between the two ends. Theta is the change in rotation between the two ends over the length L which is subjected to a twisting moment T. Now, if we compare this particular expression with the deformation that we have derived in module 2, wherein when the bar is subjected to a load P, we have said delta is equals to P L by A E, which is the deformation. So, here the deformation in terms of rotation which is analogous to P, we have twisting moment T, the length of the bar, and in there we had the modulus of elasticity, here we have the shear modulus, and in place of cross sectional area, here the polar moment of inertia J comes into picture. So, this is the rotation theta that we can have. Now, if we like to relate the shear stress with the twisting moment, because of the application of the twisting moment, the shear stress gets generated, and if we like to evaluate that, now we had seen tau is equals to G d theta dx times rho. Now, from this particular expression we can see that d theta dx, this particular expression gives us d theta dx as equals to T by G j. So, if we substitute for d theta dx as T by G j, this gives us G times T by G j times rho. So, this gives us T rho by j, or tau by rho is equals to T by j. So, this is what is the expression of shear stress which is related to the twisting moment T. Also, we have just now have seen that theta, we have related the theta is equals to T L by G j. So, from here if we write down T by j is equals to G theta by L. From this expression we get that T by j is equals to G theta by L, and from here we get T by j is equals to tau by rho. So, combining these two, then we can write down the expression for the torsion, which we call as a torsion formula as T by j is equals to tau by rho is equals to G theta by L. So, this we call as the torsion formula, in fact, which relates the shear stress with the twisting moment and also the angle of twist over the length of the member. From this equation we can evaluate that if a bar is subjected to a twisting moment, then what will be the stresses in the bar in terms of the sectional parameters that we will be knowing. We can evaluate what will be the strain once we know the shear modulus. We can find out the angle of rotation, angle of twist because of this twisting moment, how much angular deformation that a bar undergoes. Now, in the previous cases we were evaluating that when the bar was subjected to axial pull, subjected to axial force in the bar, what is the stress, what is the deformation. Now, here we are computing the deformation and the stresses of the bar when it is subjected to a moment which is about the axis perpendicular to the cross section. Okay. Now, let us look into some of the example problems based on this discussion. Now, before we go to these examples for twisting moments or the torsions, let us look into the example which I gave you last time, and probably you have solved it. Let me just quickly go through it, so that you can check your answers with this. Now, a thin walled cylinder 4.5 meter long, 500 millimeter internal diameter and 5 millimeter wall thickness is prevented from axial displacement under an internal pressure of 8.25 megapascal. Now, all you will have to do is determine the maximum tensile stress and the increase in the internal volume for the at this pressure 8.25 MPa, given the value of E as 165 GPa and mu as 0.24. Now, let us look into that how do you get the maximum tensile stress and then the change or increase in the internal volume. Now, given length of the cylinder is 4.5 meter. Now, diameter, internal diameter as 500 millimeter, the thickness of the wall is 5 millimeter, the internal pressure is equals to 8.25 MPa, and value of the modulus of elasticity E is given as 165 gigapascal, and mu, the Poisson's ratio, is 0.24. Now, the maximum tensile stress that occurs on the surface of the cylinder on the cylindrical vessel is equals to sigma 1, which is P r by T, and P here is 8.25 MPa, radius, diameter is given as 500. So, radius is 250 divided by T is 5 millimeter, and this gives us a value of 412.5 MPa. Correspondingly, the value of sigma 2 is equals to sigma 1 by 2, which is equals to 206.25 MPa. Now, if we compute the value of the strain, which is epsilon 1, which is equals to sigma 1 by E minus mu times sigma 2 by E, and this is equals to sigma 1 is 412.5 MPa divided by E is 165 gigapascal. So, 165 into 10 to the power 3 megapascal minus mu is 0.24 and sigma 2 is 206.25 divided by 165 into 10 to the power 3, and this gives us a value of 2.2 into 10 to the power minus 3. Consequently, we can compute the strain epsilon 2, which is sigma 2 by E minus mu sigma 1 by E, which is equals to 206.25 divided by 165 into 10 to the power 3 minus 0.24 into 412.5 divided by 165 into 10 to the power 3, and this consequently gives us a value of 0.5 into 10 to the power minus 3. Now, if you remember that for volumetric strain delta V by V, E is equals to delta V by V, for which for cylindrical containers we have E as equals to 2 epsilon 1 plus epsilon 2. So, epsilon 1 we have seen, which is 2.2 into 10 to the power minus 3, and epsilon 2 is 0.5 into 10 to the power minus 3. So, this is equals to 2 into 2.2 into 10 to the power minus 3 plus 0.5 into 10 to the power minus 3. So, this is the volumetric strain. This is equals to 4.9 into 10 to the power minus 3. So, the change in volume delta V, which is the which we will have to evaluate, is equals to 4.9 into 10 to the power minus 3 into the original volume, which is pi to 250 square into 4500. So, consequently, this gives us a value of 4.33 into 10 to the power 6 millimeter cube. So, this is the change in the volume delta V. So, the cylindrical container which was subjected to a pressure of 8.25 megapascal now is undergoing a change in volume, which is 4.33 into 10 to the power minus 10 to the power 6 millimeter cube. Well, now let us look into the second problem, which is in fact based on the discussions which we had today. Now, here it states that a solid steel bar having circular cross section of diameter 40 millimeter and length 1.5 meter is subjected to a torque of 375 Newton meter. Now, what is the maximum shear stress in the bar? What is the angle of twist between the ends, and the value of G is given as 1 into 10 to the power 5 MPa. This is the first part, the part 1, and in the second part, if the allowable shear stress is limited to 50 MPa and allowable angle of twist is 2.5 degree, then what is the maximum permissible torque? Now, in the second part, you note that two aspects are defined. One is that the stress is limited to 50 MPa and the angle of twist also is defined as 2.5 degree. So, constraints have been put on both sides. So, you will have to calculate the twisting moment considering that the maximum stress is 50 MPa. Also, you will have to calculate the twisting moment considering that the angle of twist cannot exceed 2.5 degree. Now, based on these two, whichever is the critical, that means the minimum of these will be the guiding twisting moment. Beyond that, if you go, then one of them will fail. So, let us look into first part, that what is the maximum shear stress in the bar and what is the angle of twist between the two ends. Now, the diameter of the bar given is 40 millimeter, the length of the bar is equals to 1.5 meter, and the twisting moment that is acting is equals to 375 Newton meter. Now, we have seen now that the expression for or the equation for the torsion is T by J is equals to tau by rho is equals to G theta by L. Now, for the given bar, the polar moment of inertia J is equals to, now this is pi d4 by 64 is Ix, and also Iy is pi d4 by 64. So, twice of that means pi d4 Ix plus Iy, which is equals to pi d4 by 32. This is the polar moment of inertia, and d being 40. So, this is equals to pi into 40 to the power 4 divided by 32, so much of millimeter to the power 4. So, this gives us a value of 2.513 into 10 to the power 5, so much of millimeter to the power 4. Now, what we need to evaluate is the shearing stress tau for the given twisting moment. So, we take the first part of this equation, where we write tau as equals to T times rho divided by J. Now, the twisting moment T here is 375 Newton meter. So, 375 into 10 to the power 3, so much of Newton millimeter, multiplied by rho. Now, rho, if you remember, is the radius. Now, diameter given here is 40. So, that is 20 divided by J, which is 2.513 into 10 to the power 5. So, this gives us so much of Newton per millimeter square, which is megapascal, and this gives us a value of 29.84 megapascal. So, this is the value of the stress tau. This for the given twisting moment T, the shear stress is 29.84 megapascal. Also, we need to evaluate the value of the angle of rotation theta, which is tau by rho is equals to G theta by L. So, from this tau by or since the twisting moment is given, let us take T by j is equals to g theta by L. So, theta from this expression we get as T times L by g j. Now, T is equals to 375. So, theta is equals to 375 into 10 to the power 3, so much of Newton millimeter. Length is 1.5 meter. So, it is 1500. G is given as 1 into 10 to the power 5 megapascal into J we have computed as 2.513 into 10 to the power 5. So, 2.513 into 10 to the power 5 is so much of radians, and this comes as 0.0224 radian, and this is equals to 0.0224 multiplied by 180 by pi will give so much of degree. This is equals to 1.28 degree. So, this is the angle of rotation and this is the stress. These are the two parameters that we had to evaluate. So, shear stress and tau is given by this. Now, let us look into the second part, wherein we got to compute the value of the twisting moment where for limiting stresses. Now, the limiting stresses are the tau is limited to 50 megapascal and the angle of twist theta is 2.5 degree. Now, for these two cases we will have to find out what is the T. Let us call this corresponding to this T as T1 and corresponding to this T as T2. So, if we compute T1 and T2, lesser of these two will give us the value of the guiding twisting moment. Now, from the first that T by j is equals to tau by rho. From this if we compute the value of T, which is equals to tau times j by rho. Now, tau here given as 50 MPa. So, this is equals to 50 multiplied by j, which is in terms of diameter, which is pi d4 by 32. So, pi into 40 to the power 4 divided by 32 is the j, and rho is d by 2, which is 40 by 2. So, this gives us a value of, if we compute this T, we get from here as 628.32 Newton meter. So, this is the amount of twisting moment that is necessary if we have to restrict the stress up to 50 MPa. If we go beyond this, the stress level will exceed 50 MPa. So, we will have to, we cannot go beyond 628.32 Newton meter as the twisting moment, because if we go beyond that, then the stress level will go beyond 50 megapascal. So, if we have to restrict the stress in the bar up to 50 megapascal, then we will have to restrict the twisting moment in this particular value. Now, let us look into that if we have to restrict the angle of rotation to 2.5 degree, what is the twisting moment that we need. So, for the second case we have theta as equals to T L by G j. So, this is equals to, or from this we can compute T as equals to G j theta by L. Now, G is given as 1 into 10 to the power 5, j we have pi into 40 to the power 4 divided by 32, L is 1500 and theta is 2.5 degree. So, 2.5 into pi by 180, so much of radian, and this gives us a value of T. So, this gives us the value of T as equals to 731.08 Newton meter. Now, please note here that we have got now the two values of the twisting moment. One value of the twisting moment by restricting the stress up to 50 MPa. That means, if we apply that amount of twisting moment, the stress will be limited to 50 MPa. If we go beyond that value, the stress level will exceed 50 MPa. In another case, we have got a twisting moment beyond which we will have to apply up to that value. If we go beyond that, then the angle of twist will increase by beyond 2.5. Now, since we will have to satisfy both the criteria, hence the limiting value of the twisting moment will be 628.32 Newton meter. So, value of T which is to be applied, the maximum value of T which can be applied in this particular case is 628.32 Newton meter. So, this is the answer for this particular example. Now, let us look into another example which is of similar kind, but little difference that here we are defining in terms of the strain. Now, a copper rod of length 600 millimeter is to be twisted by torque T until the angle of rotation between the ends is 4 degree, and if the allowable shear strain in the copper is so much of radian, then what is the maximum permissible diameter of this particular rod. Now, this is the rod which is of length 600 millimeter subjected to a twisting moment, and we will have to see that the strain does not exceed of 0.008 in that particular rod. Then what is the value of the torque, so that what is the value of the maximum diameter to resist this much of strain. Now, let us look into the now T by J again is equals to tau by rho is equals to g theta by L. So, tau, the shearing stress, as we know, is given as g times gamma. This is the relationship between the shearing stress and the shearing strain. So, tau by rho is equals to g theta by L, or tau by g is equals to rho theta divided by L. Now, tau by g, this particular parameter we can call this as gamma. So, gamma is equals to rho theta by L. Now, rho is d by 2. So, d times theta divided by twice L. Now, here the diameter is to be evaluated d times theta is limited to 4 degree. So, this multiplied by pi by 180, so much of radian, divided by 2 times L, L is 600. So, this gives us the value. Now, this is to be limited, the strain is to be limited to 0.0008. So, this is the limiting value of the strain, and from this we will have to evaluate the value of the diameter d. So, d, if we calculate from here, gives us a value of 13.75 millimeter. Now, please note here that in this particular case the strain of the bar was limited, that because of the application of the twisting moment, the strain cannot exceed beyond a specific value. Now, to limit to that particular value of the strain, we will have to find out that what maximum diameter of the bar you can use it, and as we can see from here that utilizing the relationship between the torque and the stress and the relationship between the stress and the strain, we can find out that how much diameter of the bar can be applied. Well, we have another example problem where a solid aluminum bar of length 1.2 meter and 25 millimeter diameter is twisted by torques T acting at the ends. The shear modulus is given. You will have to determine the torsional stiffness of the bar, and secondly, if the angle of twist of the bar is 5 degree, then what is the maximum shear stress. So, these are the two parameters that you will have to define. Well, this particular problem is set for you, look into it, we will discuss next time. Well, now to summarize then, in this particular lesson we have looked into the concept of torsion in a bar of solid circular cross section. Now, here we have taken a bar, the cross section of which is a circular one and it is a solid circular one, there is no hollowness in such bar, and if this kind of bar is subjected to a twisting moment, then what is the consequence of that, what are the stresses and what deformations do occur in such bars, that is what we have looked into. And then concept of stresses and deformation in a bar of circular cross section due to torsion, and then we have looked into some examples to evaluate stresses, strain and deformation in bars of solid circular cross section due to such torsions. Now, we have some questions set for you. Now, what is the type of stress a bar encounters due to torsion? Now, once you go through this lesson, you will be able to understand this, that when a bar is subjected to a twisting moment, then what is the kind of stress that a bar is subjected to. Now, what is meant by torsional stiffness? Now, this aspect is important. Now, in fact, the problem which is example which is set is in terms of this. So, you can find out that what is the torsional stiffness and what will be the stresses and deformation due to torsion if the bar is hollow circular section instead of solid one. That means, now the cross section which we have considered here as a solid, instead of solid, if it is a tubular one, if there is some hollowness within the bar, then how you are going to compute the stresses. Now, we will have to see that whether we can apply the same formulae which we have derived here for solid sections, based on that whether we can compute the stresses in a bar which is hollow or which is having a hollowness in the cross section. Well, the answers for this will be given in the next lesson and we will discuss that. Thank you very much for your attention.